Hey, welcome back to Math 7195, Unit 4, video number 2. Today we'll be discussing more continuous probability distributions. So we'll be moving on from the simple normal distribution and introducing the log normal distribution, exponential distribution, and the Weibull distribution. I think that should be enough for one day. We'll jump right into this. Continuing on in our notes here, we're on page 17, the log normal distribution. Oftentimes we'll see this new distribution. I see it with my mining students. The grade of ore often has a log normal distribution. The other time I see it is when we are talking about multiplying different distributions together. So when you have successive multiplication of distributions, we'll often come up with applications that involve this log normal distribution. The way it works is you have a variable x. It's log normally distributed if you transform it using the natural logarithm. If that turns out to be a bell curve, well, then we say that x is log normally distributed. So if the log of all your values follows a bell curve, then you have this log normal distribution. So it's a fairly basic transformation where we're just going to take all our values and take their log. So our function from the normal distribution basically still applies. We're just replacing x with the natural log of x. We'll replace mu with the mean of the transformed data, and we'll replace the standard deviation with beta. That's the standard deviation of the transformed variable. So imagine you have a big data set, we call it x. If we take the natural log of x and we calculate the mean of those natural logged values, that gives us this parameter alpha. And if we take the standard deviation of all those natural logged values, we get this parameter beta. We can then get the mean of the original distribution. Doing some algebra, we can state the mean of x in terms of an exponential function. It's e raised to the alpha plus beta squared over 2. That's like all in brackets like that. It's e raised to all of that. And the standard deviation or variance, this is e raised to the 2 alpha plus beta squared, in sort of in brackets like that. And then take that multiplied by e to the beta squared minus 1. We have a function in Excel that handles these probabilities, but basically we would have to find the area beneath, this density function, which can be done very easily because we can just do a transformation and use a z distribution. Looking at the log normal distribution, its shape changes depending on what your parameters are. As alpha and beta vary, we get different shapes. Sometimes it looks it often looks skewed to the right. Sometimes it looks like exponential decay here when it's like when beta is bigger than 1. How do we do these calculations? Typically, when we had a normal distribution, we calculated z-scores, and then we were able to look things up in our z table, and that was x minus mu over sigma. Well, now we have a new, variable here. We're going to do a transformation on x, so we'll have the natural log of x minus the mean of those natural logged values, which is alpha, divided by the standard deviation of those transformed variables, beta, and then everything is the same. we can just look things up in our Z table. So the log normal distribution's, really easy to use. Basically, if we're already good at finding probabilities using the standard normal distribution, we'll have no trouble with log normal distribution. We just have to recognize that the problem is log normal. Here's a little example. We have power consumption over some period of time is a log normal distribution random variable. So the power consumption is megawatts per hour. And I guess we've been studying this, process for a while. We've been able to come up with the parameters for alpha and beta. This is a typical, textbook type question, where these values just sort of magically appear. We'll come up with a way to estimate them in the next example. But let's just start with this. I plotted what a distribution with alpha is 7.5 and beta is 0.3, just so you can get an idea of what this looks like. And then we ask some questions. For example, what's the probability that the power consumption is above 1,500 megawatts per hour? X is a log normal variable with parameters 7.5 and 0.3. So we solve this thing just by doing a transformation. Just like we did when we had non-standard normal distributions, we converted them into standard normal distribution. Here we have a log normal distribution and we convert it into standard normal distribution. To solve x greater than 1,500, we convert it to its z-score. So when z is greater than the natural log of 1,500 minus the mean of those values, which is then 7.5, and divide that by the standard deviation of those transformed variables, which is the 0.3. Remember, z is the natural log of your variable minus alpha over beta. The calculation here, we have z greater than negative 0.62. If we look at this, what are we trying to find? I guess 1,500 is, say there, and we're looking for the area to the right of it, roughly. So I expect this to be a fairly high probability, just looking at our, we have a pretty accurate graph, and then I, guesstimated where 1,500 was. So I'm expecting this to be over 50%. When we did the conversion, we want the probability of being greater than negative 0.62. I'm changing my pen here. There. We want z greater than negative 0.62. So that's down here somewhere. And we're looking for then this area is equivalent to the area that's, shaded up above. To calculate that, I can do the area to the left of positive 0.62. Notice I didn't do 1 minus this. I'm just doing a little, flip over the axis here. I'm saying that the area above negative 0.62 is the same as the area below positive 0.62, because now I'm going to go and look that up in my Z table. So we go to our Z table, and we find that 0.62 gives us a value right here of 0.7324. So power consumption is above 1500 approximately 73% of the time. There's a part B there. It's asking for the median value. So we're looking for the value on the axis there that separates the bottom 50% from the top 50%. To figure this out, we want the probability that x less than the median, how about I call it the 50th percentile, that will be 50%. 50% of our values are smaller than some number. Well, the z-score is the natural log of that value minus 7.5 over 0.3. That curve up above there, it looks something like this. We're looking for the spot. That's probably not it. We're looking for the spot that's in the middle of the area there. This area here needs to be half of it. Because that'll give us the median. So this is the spot on the axis, this P50, the 50th percentile. The z-score that goes along with this must be 0, right? If we look at our z distribution, 0 is in the middle, so the area to the left of 0 is 0.5. So our z-score that corresponds with this is 0, so we just say 0 equals the natural log of the 50th percentile minus 7.5 over 0.3. Myself a little extra space here. Since I'm writing kind of large. Now we just solve this equation, e to both, or I guess we can say 0 equals the natural log of the 50th percentile minus 7.5. So e raised to the 7.5 equals the 50th percentile. So I get 1808 equals the 50th percentile. When the power consumption, I guess I should put some units in there. It's megawatts per hour. Half the time the consumption is above 1808 and half the time it's below it. And if you want to solve part C there, part C is asking what's the mean value. It won't exactly match the median because this is skewed, right? We know that if we have a distribution that's perfectly symmetric, that the mean and the median should be the same. But it's not horribly skewed in this case, so I'm expecting it to be fairly close to this. Because it's skewed to the right, I'm expecting it to be a little bit larger than this. Let's see. Our formula for mean is just e to the alpha plus beta squared over 2. And I just substitute the values in there. So alpha was 7.5, beta was 0.3, and we get a value of 1891 megawatts per hour. So not too bad. Excel is even nicer for these things. It has built-in log normal function. If we're trying to solve these things with Excel, we could open Excel. I have some examples here. And I have example number 5 already set up here. The function in Excel to do log normal distribution is lognorm.dist. It takes 4 parameters or 4 inputs, x, alpha, beta, and then that flag for whether it's cumulative or not. And it will always be cumulative unless you're just trying to plot the curve. This again gives you the area beneath the curve to the left. So in our example, we had what's the probability of being above 1500? So we do 1 minus below 1500, and that function is just given here. Log norm dist 1500, alpha 7.5, beta 0.3, and yes, it is a cumulative distribution. And we matched the answer that we had before, and we didn't even have to calculate any z-scores or look anything up in any tables. The median uses another log function. When you use the dist function, you get probabilities. When you use the inv function, it gives you the value on the axis. So in our case, we wanted the 50th percentile, so I put 50% in alpha and beta, and it gave me the value on the axis of 1808. For mu, calculating the mean, there is no built-in function. I had to just use the function or the formula that we have. It's exp is how you do, exponential with natural log base. So this exp means e raised to the, and then whatever you put in brackets. So in this case, it's 7.5, alpha plus beta squared over 2. And we did agree with the same answers. We saw that because of the skewness, that the mean was a bit larger than our median. So yeah, it's pretty fun to do them in Excel. And you're certainly welcome to do them that way. So we can continue on with this. I thought, where the heck did alpha and beta come from? So I thought I should do a quick example with you guys. It's still a log normal problem, but it's a real world one where maybe you don't know what alpha and beta are yet. Suppose a geologist goes up to the Yukon and gets 1,288 soil samples. And then they study each sample and determine the concentration of chromium. And that concentration, I think, is measured in parts per million. So here are the results. A histogram is given. The 1,288 values were plotted on a histogram, so we could see the general shape. And we can see that this sort of looks like that log normal shape that we saw in the log normal plots. So I'm trying to come up with a way to estimate alpha and beta. Well, I have my 1,288 values. If I take the natural log of all of those values, I can then find the mean of the natural logged values. And that's what this A is here. And I can also calculate the standard deviation. Basically, my units are natural log of parts per million because I took the natural log of all of the data and then calculated mean and standard deviation. After doing the natural log of all of the values, I plotted that as well to see if I did get a bell curve, and it's not terrible. It's pretty close. I mean, this is real world data. I actually went to the mining department to get this data. So it's cool that it is actually working out okay. Now, if I say that this is close enough to a bell curve, then I can say that, well, why don't I call A alpha and B beta going forward, saying that, well, it's the best that I have for those, they're the best estimates I have for those values. Certainly, if I rounded them, it'd probably be fairly accurate to say it's, 4 and 0.5, for example. Maybe I shouldn't be listing them to, 3 decimal places. Now we can do a problem where we could do modeling. What percentage of these values would we expect to be under 130 parts per million? Where X is the concentration. Again, we can just do the transformation and look it up in our table. It's the natural log of 130 minus our alpha, which we estimated to be 4.282, and our beta to be 0.530. I'll just leave the extra precision in there just to keep, we can round later. We get a z-score there then of 1.10, and then we can look that up in our z table. 1.10 is 8643. So 86%, almost 87%. 86% is under 130 parts per million, give or take. We can estimate the mean and standard deviation now with our alpha and beta. Again, these are just sort of plug and chug type things. Our alpha was 4.282. Our beta was 0.53. I get 83.3 ppm. And we could calculate the variance. Again, just plug those numbers in. I get 2255 ppm. Or if you take the square root of it, I get 47.5 parts per million. So quite a bit of variation there. If your mean is 83 and your standard deviation is 47. It turns out that the actual values for the mean were 82.6 and the standard deviation was 42.8. We were pretty close, but remember, we're using a theoretical model, and this data didn't exactly follow that model. It was pretty close, but not perfect, and that's why there's a difference between those two. But I just wanted to show a quick example there where these parameters just don't magically appear. You have to collect some data and have some idea of the shape of the thing before you can start, building a model. We can move on to the next probability distribution. It's another continuous one. It's called the exponential distribution. It's often used in queuing. Remember, we used the Poisson distribution to deal with queuing as well. It was we used it to model how long the line was in a queue. How many people are in the queue at any given time. The exponential distribution is used to model how long it takes someone to service a customer. So if you're building a queue model for, say, a bank, you have to keep track of the arrivals of people at the bank, but you also have to keep track of how long it takes, the people at the counter to service those customers. And then you can start estimating things like the length of the line and how long a customer would have to wait. So exponential distribution is very handy in that situation. It has a nice function. 1 over beta e to the minus x over beta. And that's a nice function because it's very easy to integrate. We're really good at integrating e to the x. So we can find the area beneath this curve without having to use a table. Hooray! We can just solve these problems directly. In fact, we essentially can just build the formula right now. If you want the integral, if we want f of x for this thing, we'll go from 0 up to x of 1 over beta e to the t over beta dt. And that'll give us the area beneath that curve. Sorry, it's negative for the function there. So, when you do integration, you could do some sort of substitution, or you could probably just guess. I'm guessing that it's e to the minus t over beta. And then if I were to take the derivative of this, I would get negative 1 over beta in the chain rule. But I want it to be positive, so I'll just adjust it with a minus sign. And then we can use the fundamental theorem there. It's negative e to the negative x over beta minus negative e to the 0 over beta. And that simplifies to 1 minus e to the minus x over beta. And now whenever we want the area beneath that curve, we can just use this formula. We don't need a table or anything. The mean of this thing is whatever that beta is. So say I can service 10 customers per hour. My mean is 10 customers. So that's what beta is, 10. And then the 1 over beta is the rate. And the variance is really nice. The variance is beta squared. So the standard deviation is beta as well. The mean and the standard deviation are always equal. Here's just one example. I just said, what if beta is a half? Then my function becomes, 1 over a half, which is 2 e to the minus 2x, and I plotted it. You can see that the intersection point here is at 1 over beta. And it always will be. And then we're just finding the area beneath this curve. That 1 over beta is the rate at which we do this service, and beta is the average that we service during that time period. I already did the integral. I was so excited I couldn't wait. So we've already derived this formula up above. So we found that it was 1 minus e to the negative t over beta on your formula sheet. So you can just use this now that we've derived that. Although that integral is so easy that you probably wouldn't mind doing that one. So yeah, there we go. Sometimes we say this exponential distribution is memoryless. Basically, it has a constant rate. That the rate at which the customers are serviced is always the same, regardless of what time it is. It doesn't matter if I've already serviced 10 people today. I'm not tired. I'm still working at the same rate. They say it's memoryless. sometimes. Here's the classic bank teller example. Bank teller sees an average of 60 customers per hour. Wow, busy guy. On a 1 minute basis, then his rate is, 1 customer per minute. So his 1 over beta is 1 customer per minute. His mean is 60 per hour. But the question started talking about minutes. So we converted our rate from per hour to per minute. Again, always adjust that rather than the time frame. So we're trying to find the probability that it takes less than half a minute. Probability that the time is under 1/2. Well, we've already derived the formula. F of t is 1 minus e to the minus t over beta. So our beta here is 1. So we have 1 minus e to the negative 1/2 over 1, which is 1 minus e to the minus 1/2, which ends up being 0.3935. And this is so easy, you probably don't need Excel to do it, but Excel does have a function. It's expon.dist, and you input the 0.5 or the half, and then you put in, I think you have to put 1 over beta in. So in this case, it's 1. It's hard to see what beta and 1 over beta are both 1 in this case. And then cumulative, you get the same result. Find the probability it will take between 1 and 2 minutes. Set it up. The time is between 1 and 2. Again, it doesn't matter if you include the endpoints or not, because it's continuous. If it were discrete, we have to be very cautious about, what do we mean here by between? But in the discrete case, it doesn't matter at all. So we're finding the probability of being under 2 minus the probability of being under 1. The function works to the left really well. This thing looks like this. This is 1. 1 over beta equals 1. And we're looking between 1 and 2. So we're trying to find an area like this. I didn't draw it to scale or anything. So we just substitute 2 into our formula, 1 minus e to the negative 2 over beta, and then subtract 1 minus e to the negative 1 over 1. Punch all that in. I guess we get what? I ended up with 0.2325. If you're in Excel, you would just use expon.dist twice. Let's take a look. I think I already did this example somewhere. Let's see, example 7. We had our 1 over beta, which was 1, or beta equals 1. See the syntax? It's x, 1 over beta, and cumulative. So we wanted t under half a minute, so it's expon.dist, exactly what we wrote. If you want between 2 and 1, or between 1 and 2, we do the less than 2 minus less than 1. So expon.dist with 2, and then expon.dist with 1. And you get the same result that we saw before. So again, Excel is pretty handy for this, but not that much faster than we are probably with our calculator. Another example here, which is another exponential one. We have a watch. It needs to be reset on average every 50 days. So it's an old pocket watch, and you have to wind the thing up every 50 days. Find the probability that such a watch will have to be reset in under 20 days. So in this case, our beta is the mean, so 50 days. So the rate is one reset per 50 days. And now we can just solve this thing. We want the probability that the time is under 20. So it's 1 minus e to the negative 20 over 50. I get 32%. 33%. Roughly 33% of the time we'd have to reset this thing in under 20 days. Probably don't need to look at the Excel for that, but there it is. Again, I shouldn't, this is probably a typo. This shouldn't say beta, it should say 1 over beta. Beta is 50. So yeah, it would have been better not to do this. Exponential, expon.dist, we input 20 because we want 20 or less. That's our rate. So it always is asking for the rate. And we get the same result. The next one, we have one more distribution here, the Weibull distribution. It's a generalization on the exponential. It allows us a lot of flexibility. You can model a lot of things using the Weibull distribution. It has a bunch of 2 parameters, alpha and beta. And a special case of this distribution is the exponential distribution. But we can use this distribution for many, many different things, similar to how we estimated. Remember, we had 2 parameters for the log normal. We have 2 parameters for this Weibull distribution as well. We can, gather a bunch of data to come up with estimates for alpha and beta, and this model fits a lot of situations. And it's nice because it's integrable. It's a bit of a pain to integrate. You have to sort of know a trick to beat this function. We want to integrate this function, from 0 up to some point. I said some point A. To solve this integral, that you can do a little transformation. You might not have thought of on your own, but it's been a little while since we've done calculus. If you look in the formula here, you'll see there's an x to the beta, and there's an x to the beta minus 1, which is pretty nice when you think about, the derivative of the exponent here ends up being what's down here. I'm going to do a little substitution this time. Let's let y equal x to the beta. So then dy is beta x to the beta minus 1 dx. If we just differentiate both sides of this thing, you'll see that these terms show up in here, the dx, the x to the beta minus 1, and the beta. So we can replace those 3 pieces with dy. And then what's still sitting there? Well, alpha is still there. And the x to the beta can be replaced with y. And now we have an integral that is just in terms of y. Alpha is just some constant in there. So we're basically just, integrating e to something. We have to change our limits of integration there. If we're going from 0 up to a, if this is our our transformation, when you put 0 in here, y is still 0. But if you put in a, then you get a to the beta, and that's why the upper limit is a to the beta. So now we can just integrate that thing. Again, you just guess. I just guess it's probably e to the minus alpha y. But if I take the derivative of this thing, I get negative alpha. So I need to adjust it with a minus sign. And then fundamental theorem. Similar to the exponential, we get 1 minus e to the negative alpha a to the beta, where a is the upper limit, or what you're trying to find a value less than or equal to. So now we have this formula. We don't need to integrate that one again, thankfully. But that one wasn't too bad either. We're going to see this function used when we do some modeling of, we're going to do some reliability. And this is a model for, the time to failure of, a certain product, say. So that's another reason to use F, F for failure. We'll see examples of this in the next unit. Right now we're just introducing old Weibull. The mean of the Weibull distribution is getting pretty mathy. It's alpha raised to the negative 1 over beta times the gamma function of 1 plus 1 over beta. And the variance involves gamma function. And then I reminded you what the gamma function was. It's kind of a nasty integral. Often it's one we have to numerically integrate. But it does have one cool property, that when you do gamma of an integer, then it's super easy. Like I said, gamma of psi, where psi is an integer, ends up just being psi minus 1 factorial. So the function is recursive as long as you are, finding positive integers. The gamma function evaluated at 7 is 7 minus 1 factorial, which is 6 factorial. So this nasty looking, integral, if you're evaluating it at 7, is just 6 factorial. Of course, if you want to do gamma of 7.1, then you got your work cut out for you with this thing. Most likely you'll have to do some numerical methods, or use some software, Maple or something, to give you a good estimate for this. And then that would allow you to calculate the mean and standard deviation of a Weibull. So Weibull is great because it's so general and works for everything, but sometimes the math is a little bit ugly. I'll try to come up with examples where the gamma function ends up being a nice positive integer, so that we can just take advantage of this fact. There is a function in Excel for the gamma function, but it doesn't work exactly the way we'd expect it to be. Or the gamma function works okay. It's the Weibull distribution that doesn't work great in Excel. The parameters that Excel uses, it doesn't use alpha and beta the way that we do, and I'm just following a textbook. It uses a different version for alpha and beta. So we'd have to do a transformation to use Excel, which maybe we'll do that later just for fun. Yeah, I think that's a good place to call it for this lecture. We'll discuss this Weibull distribution as we do some examples when we do reliability. So you guys all take it easy, and I will see you next time.